Okay, so basically this is your week 13 review. It's going to go over a few concepts I think in the homework that are a bit complicated, and as well a mass percent calculation, because that was something that we had a lot of trouble with in that last lab, and I want to make sure because it does come up in the exam and it also will come up in this week's lab, so I want to make sure we get that super solid before we move on. So this review is going to be over coordination complexes, especially salts, because I think those are very confusing because it's hard to find the central atom. So I'm hopefully going to kind of give some clue in on that. And then also again working with high spin, low spin, weak field, strong field, kind of seeing how those terms can be used interchangeably, and then how those apply to things like color, and also from color, and then of course magnetism. So hopefully we can grind those things in because they are going to be on the exam and they are slightly confusing. So without further ado, so a mass percent calculation, that's what I really wanted to go through because it's from last week's lab and it's when you have a given molarity. And so you're going to have the moles of the acid in some sort of volume, and you're going to take the molarity times the volume to get the number of moles. And when you have the number of moles, then you're going to have to go back, and it's going to tell you also the amount of grams that you have in that given volume. Now we know that molecular weight is just grams over moles. And so then I go through and I put the weight in 100 mil divided by the moles to give me the mass percent. And to give me the molecular weight. And then from there I can work forward to get the mass percent. Because once I have the molecular weight, it's theoretical. And then I can work forward to get the mass percent by basically taking what I got divided by what I should have gotten to get what I essentially would need. So be able to work backwards from that, and please email me if that does not make sense. So this is my molecular mass here, and then I would go through again with the number of moles and make sure that they would match up. Does that make sense? Okay, and then multiply by 100 because it's a percent. Okay, so pause the video and read through these because I'm not going to read for you. You all know how to read. But basically what I wanted to kind of highlight here, sorry I had to readjust my computer. What I wanted to highlight is basically the coordination number is the number of donor atoms. And so that means how many things are basically connected to that central ion. And sometimes it's hard to identify because it's hard to know which is the center and which is just a spectator. And rule of thumb, central atoms are usually metals. And by metals, I mean transition metals, not the alkali or the earth metals. And they're normally something in a bracket. So those are the things that you're going to be looking for. The other thing I wanted to comment on is monodentate ligands are usually anions, and that's what it means like halides. So F minus, I minus, etc. NO3 minus, PO4 minus, etc. And they're all simple Lewis bases. And that can also apply to bidentate and tridentate ligands, but they are just attributing a different number of electrons. So by simple Lewis bases, it means they give one pair of electrons. But tridentate and bidentate, as we can see, bind multiple times to the center and therefore can give more than just one electron to that bond. So that's something to keep an eye on. Okay, so classifying each of the following compounds by their coordination number. So I'm just going to pop up one of the first complexes, and I just worked through showing the anion is -1, and therefore the charge on Ag is +1, and therefore it's going to have 2 chlorines attached to the center. And the same thing is kind of true of the cyanide ion since it's also -1. So it's going to have a coordination of 2, and that's because there's 2 cyanides attached. With mercury iodine, same idea, except there's 3 iodines attached to the central ion, so therefore it's going to have a coordination of 3. The same with all these others. We can kind of see these very clearly. These have so and so many. You work past because these are all within brackets. But what happens when we have something that's a salt, like this barium iron bromide? Well, basically, we break this down into just 2 ferrous bromides that make up the salt with barium, and therefore it has a coordination of 4. And then we can do the same thing here with the cobalt fluorine salt, in that you again have a central atom with 6 ligands, and then the potassium is just a spectator. So again, we'd put that in 6. So I want you to kind of go back and pause the video and kind of look through these and ensure that that made sense. But basically what I'm trying to get at is when you have that central atom, that central atom is going to be the one that attributes to the coordination number. And the barium, which was an alkali earth metal, and that potassium, that was an alkali metal, those are all spectators, and those are just attributing to a salt, and they are not attributing to the coordination of that central metal. So be sure to pause that video, go back through those, see if you can get the same answers I did, and let me know if you didn't. And maybe I'm wrong, or maybe you're wrong, but hopefully we can work out who's wrong and work it through. Okay, now the next thing I want to know about is high spin versus low spin. So high spin basically has more to do with the change in energy. Now I've shown these both as the same energy splitting because it's not as exaggerated as a lot of people like to show it. But what the idea about high spin is that it's easier to fill and move up into the higher energy levels because the energy levels are closer together. And because those energy levels are closer together, it's easier to move into them. This can also be said for weak field ligands. Weak field ligands tend to be high spin complexes. And the opposite can be said in that strong field ligands tend to be low spin. But the idea is that the weak field and strong field is more attributed to the ligands, while the low spin and high spin is attributed to the complex, specifically an octahedral complex, and how close together those orbitals are. So as we can see and you're going to see in the next example because I've exaggerated a bit better, but the low spin is because those energy levels are actually much further apart. Meanwhile, the high spin, those energy levels are closer together, and therefore it's easier for the electrons to go up and down and through these different energies. So that's why. So hopefully we can see that in this next example. So I have a 5D and 5G complex, and I want to know why one is more brightly colored. And so I can see that they're both in group 7, so they're both going to be D7 sort of elements. And then I can see that this one has a phosphorus and this one has a Cl2, so it's the only difference between them. So I'm going to go through and count the electrons here to figure out how many are for 5D. And I note that also there's many ways to write this, because there was another thing that came up on your homework, which is about geometric isomers, where we have all of these ligands attributing to the central atom. But I wanted to point out that these are all still the same. They are just geometric isomers. Some are trans and some are cis, but they still are the same, just have different elements. So we count up all these. I noticed that this is a 2-electron donor, however it's neutral. The ACAC, which is that double oxygen there, is 4 electrons, but it's bidentate. Ooh, bidentate. Help. Let me click. I'm just going to leave it at bi, period, and leave it as a annotation. So it has 4 electrons, but it donates a minus charge twice, and the CN is -1, so I get 3 plus on that manganese. So therefore it goes from D7, and that's, again, the phosphorus is neutral, and so that's the 3 plus comes from 7 minus 3, giving us a total of 4 electrons to work with. So now I have 4 total electrons to play around with in my energy splitting diagram. But I note that that CN right there is very much a strong field ligand, and therefore, as well, manganese has a greater splitting. And because of that greater splitting, that's going to make it a low spin complex. And that low spin complex is also going to mean that I'm taking forever to write this. I thought I'd write this quicker. Is going to mean that it's also hard for those electrons to pop up because the orbitals are further apart. And that's because they have a large energy splitting difference. So we'd identify this for 5D. That's what this complex is. Now, say I want to look at 5G. 5G is rhenium, and it has 2 things going for it. So first of all, rhenium is also in this D7 group, so same as manganese, except it, unlike manganese, is going to be a high spin complex, and as well has a weak field ligand, and 2 of them. Now that Cl2 again is a neutral side, and there's 2 of them. And it's neutral because Cl2 is chlorine gas, so it's not necessarily contributing electrons to that rhenium. It's mostly neutral. And then that ACAC, again, giving 2 negative 1 charges, and that CN is giving a -1, so overall I get a 3 plus rhenium, and 7 minus 3 gives me D4. So that all's counting up right there. Makes sense to me. Again, I have 1 weak field one strong field ligand versus 2 weak field ligands, so overall I get a weak field complex. And as well, because rhenium is a larger transition metal, it's going to be then high spin complex, meaning a smaller energy difference, and therefore it's going to have more unpaired electrons, and therefore the rhenium complex will be more brightly colored, because we see that these electrons in the manganese cannot reach the higher energy levels and therefore will remain paired. Meanwhile, in the rhenium complex it can, and therefore they will all be unpaired, and therefore it will be more brightly colored. And then we assign that to 5G. So let me know how you guys get on with brightly colored and also making the energy orbital splitting diagrams. This is very important because it is something that comes up in the exam multiple times. So let me know how those are coming along, and I will see you guys next week. Alright, and also let me know about the exam and how you'd like your exam review. Awesome. Okay.